In this lesson, we're going to do a quick review of the stuff from chapters 14 and 15, and then you should be pretty much ready for your final exam. So, the linear relationship between the average stopping distance in feet of a car when the brakes are applied and the vehicle speed in miles per hour is given by this regression equation. So, first of all, what is the value of the slope of this equation? And write a sentence that explains what this value shows about the linear relationship between speed and stopping distance. Okay, so first, the slope is 5.67. And the best way to think about this is it's units of y over units of x. Okay, so y is distance, so feet. X is speed in miles per hour. So what this tells us is that if speed goes up by 1 mile per hour, stopping distance also goes up, or increases. So stopping distance increases by 5.67 feet. This is why it's recommended if you're going at a higher speed that you not follow people so closely. It's the mathematical reason why tailgating is bad. So predict the stopping distance if you're traveling at a speed of 70 miles per hour. So y hat will equal minus 44.2 plus 5.67 times 70. So minus 44.2 plus 5.67 times 70 is 352.7 feet. Suppose that the stopping distance for an SUV is 400 feet. What is the residual for this particular car? And I guess we're going to assume that we're going 70 miles per hour. I would have to specify that. So remember, the residual is y minus y hat. So 400 minus the previous answer we had of 352.7 is 47.3 feet. So this particular SUV needs 47.3 feet more to stop than average. Oh, explain in words what the residual in part C indicates about the stopping distance for this car. So the stopping distance for this SUV is 47.3 feet more than average. Okay, the regression equation y hat equals -3 plus 0.351 height describes the relationship between handspan and height, and the sample consisted of 167 college students. When testing to see if the true slope is 0 versus the true slope is not 0, we found that the p-value was 0.001. So question 1, is the observed relationship statistically significant? So the answer to that is yes. As your p-value is less than 0.05, the relationship between handspan and height is statistically significant. And that's what it means in the context of the situation. So that's kind of both questions. So yes, it's statistically significant, and that's the relationship between handspan and height. Okay, the value of r squared was given to be 54.7%. Write a sentence that interprets this value. So this is the proportion of a variability in y that's explained by x. So we have 54.7% of the variation in handspan can be explained by height. Okay, a regression equation relationship between body temperature and age is given as y hat is 98.6 minus 0.0138 times age. What is the predicted temperature for someone who is 31 years old? Well, y hat is 98.6 minus 0.0138 times 31. Which is 98.1722 degrees Fahrenheit. So the standard deviation from the regression line in this example is about 0.7 degrees. Use the empirical rule to give an interval that describes body temperature for about 95% of the population of people who are 31 years old. Okay, well, the average temp of a 31-year-old is 98.1722. 95% of 31-year-olds will be plus or minus 2 times 0.7 from that number. So let's just make it 98.17, because that's good enough. Plus or minus 0.7 times 2. So that's 98.17 plus or minus 1.4. So that interval is 96.77 to 99.57. Would it be unusual for a 31-year-old to have a body temperature of 96 degrees? Well, our 95% CI from the previous example was a 96.77 degrees to 99.57 degrees. And since 96 degrees falls outside this interval, this person would be in the bottom 2.5%. And I think that means yes, this would be unusual. And specifically, it'd be unusually low. Pretty much once you're outside that 95% confidence interval, that does mean something special is going on. All right, a sample of 43 college men was used to determine the regression equation. Weight is negative 318 plus 7 times the height. Weights were measured in pounds and heights were measured in inches. The standard error for the slope was given as 1.581. Calculate an approximate 95% confidence interval for the slope of this population and write a sentence that interprets this interval. Okay, so our 95% confidence interval will be given by the slope plus or minus 2 times the standard deviation. Okay, so on the low end, 7 minus 2 times 1.581 is 3.838 to 7 excuse me, plus 2.2 times 1.581 10.162. Okay, so now we can say with 95% confidence, and this is a slope, so weight increases, because remember that this is change in y over change in x, and y is weight, and x is height. So weight increases between 3.838 pounds to 10.162 pounds for every 1 inch increase in height. So if your height if you get 1 inch taller, your weight should go up between 3.8 pounds and 10.162 pounds. So it has been stated that for each 1 inch increase in height, average weight increases by 5 pounds. Does the interval computed in Part A support this statement? And the answer to that question is yes, as 5 is included in the interval. It is a plausible value for the slope, so the true m. So the data for this exercise are from a sample of 12th graders collected as part of the 2001 Youth Risk Behavior Surveillance System. So the students were asked how often they wear a seatbelt while driving, and one question is, are the men different than the women? So find the row percentages for females and row percentages for males, and let's compare them. So female, male, almost always, rarely. Okay, so of the females, 950 out of 1,050. 950 out of 1,050 is about, let's say, 90.47, so 90.5%, say almost always, and 100 out of 1,050, which is about 9.5%, say rarely, versus the men, 925 out of 1,175. That's only, 78.7%, and 250 out of 1,175 comes out to be 21.3%. Okay, so based on this table, female students appear to wear their seatbelt more often than male students. More likely to wear seatbelt than male students. Okay, and we're going to test if this is true. So null hypothesis is that gender and seatbelt use are not related, and HA is that gender and seatbelt use are related. When you're working with these tables, you're doing a chi-squared test, and that test is by default always two-sided. So even though we suspect that females use their seatbelts more, we still have to do a two-sided test. Okay, compute the chi-squared statistic. And here, because you have a 2x2 table, you have two options. You can find expected values, or you can use the shortcut. And I'm inherently a bit lazy, so I'm going to use the shortcut. That shortcut formula tells us that the chi-squared statistic is given by n times AD minus BC squared over C1, C2, R1, R2. Okay, N is the total N, 2225, 950 times 250 minus 100 times 925 squared over 1875 times 350 times 1050 times 1175. If you put parentheses where I put them, you should be able to enter this in your calculator in one fell swoop. So 2225 times parenthesis 950 times 250 minus 100 times 925, close parenthesis squared, divided by parenthesis 1875 times 350 times 1050 times 1175, close parenthesis, go. I got a chi-squared value of 57.778, so say 57.8 is good enough. Okay, next, find the p-value range. So first note that the degrees of freedom here are 2 minus 1 times 2 minus 1, or 1. And then we look at a chi-squared table. Okay, and the biggest chi-square statistic in the degrees of freedom 1 row is 10.83, and our chi-square statistic is even bigger. So we can conclude that our p-value is less than 0.001. And the reason is our chi-squared, which was 57.8, is bigger than that chi-squared of 10.83, which is the largest value in that row. So form a conclusion and write it in the context of this situation. So we're going to reject H naught and accept HA, and we conclude that gender and seatbelt use are related. Okay, and lastly we'll do a chi-squared goodness of fit thing. So before we do that, we're going to talk about finding expected counts. So supposing we have 3 categories with the following probabilities and a sample of 500. In category number 1, we'd expect to see 0.1, so 10% of that 500, or 50. In category number 2, we expect to see 50% of that 500, so 250. And in category number 3, 40% of that 500, which would be, in this case, 200. So those are our expected counts for each of the categories. Okay, if we have 5 categories, and the probabilities are all the same, then P sub I will equal 1/5. And so all categories have the same expected count of 1/5 times 1500, or 300. The following table contains the observed distribution of the last digit of the forecasted high temperatures on December 10th, 2000 for all 150 U.S. and international cities. Compute the expected counts for the null hypothesis that all digits 0 through 9 are equally likely to be the last digits of the forecasted high temperature. Okay, well, since we have 10 different digits and they're equally likely, probability that each one is chosen is 1/10, and and the expected counts are 150 times 1/10, or 15. So we expect to see 15, 15, 15, 15 all over the place if the last digit is truly happening at random. Calculate the chi-squared goodness of fit statistic for these data. What are the degrees of freedom? Remember that the chi-squared is the sum of the observed minus expected squared over expected. Okay, so in this case we observed 11, expected 15 squared over 15. 21 minus 15 squared over 15 plus 11 minus 15 squared over 15 plus 23 minus 15 squared over 15 plus 10 minus 15 squared over 15 plus 17 minus 15 squared over 15 plus 11 minus 15 squared over 15 plus 15 minus 15 squared over 15, 13 minus 15 squared over 15, and 18 minus 15 squared over 15. Okay, and go ahead and punch that in a calculator and work it all out. 11 minus 15 squared over 15 plus 21 minus 15 squared over 15 plus, again, 11 minus 15 squared over 15 plus 23 minus 15 squared over 15, 10 minus 15 squared over 15 plus 11 minus 15 squared over 15. I'm going to run a space. Okay. Plus 13 minus 15 squared over 15 plus 18 minus 15 squared over 15. So I got a chi-squared statistic of 15.6 repeating, so about 15.7. Note that the degrees of freedom here is number of categories minus 1, so 10 minus 1, or 9. Okay, state the p-value range. So my chi-squared statistic was about 15.7, and my degrees of freedom was 9. So looking at my table, that puts me between 15.63 and 16.92. So my p-value, 15.63, corresponds to a p-value of 0.075. So that's a chi-squared of 15.63. And on the low end, 0.05, and that comes from a chi-squared value of 16.92. And probably your p is going to be closer to the 0.075. But anyhow, your p-value is bigger than 0.05. So you failed to reject H0, and there's insufficient evidence to conclude that some numbers are more likely than others. And that's it for the semester. So good job and good luck studying for your final exam.